already. My name's Vanshree Bhalotia. If someone doesn't know me, I am at the EPO department and I do education and public outreach at NRAO. So my dog has a strange name. It's Twirling, Twinkling, Little Star. Your heartbeat found us from afar. It's very poetic, if I'm so humble to say that myself. But I just want to take a word from this title, the word twinkling. So what is twinkling? We know what's twinkling when we look up at the sky and we see stars twinkle. And many of us in the room, since we are all mostly astronomers or astronomy affiliated, we know that the Earth's atmosphere is what causes this twinkling. So stars are actually spherical and they're round, but they look like stars because of the twinkling. So the star shape that stars have isn't real. Real stars are round. And so unfortunately, the Earth's atmosphere makes these stars twinkle. But what if I told you that stars twinkle in space too? That there are stars that if you were an astronaut and you went up to that star, you would see the star quaking, and this quake would look like a gentle, like twinkling. So stars twinkle in space too. And the only thing is, if you did look at a quaking star through the Earth's atmosphere, the distortions by the Earth's atmosphere are so huge that you wouldn't be able to differentiate between a quaking star versus a non-quaking star. So that's the little bit about twinkling. But today my talk is about a twirling and twinkling star. So the twinkling that I'm referring to is those quakes, is those oscillations that happen in space. And the twirling that I'm referring to is like the star rotating. So that's what you see in this image here, a very scientific image of this star rotating as it's quaking. The wavy things on the surface are the quakes. So this rotating quaking star is a new sort of thing that we've discovered, right? But the idea of these types of celestial bodies has existed for millennia. So I'm just going to take a little dive into this because I think it's very relevant for the place we all live in. So this concept is called the music of the spheres. So earlier in ancient Greece, the Pythagorean brotherhood existed, and they believed that everything is interconnected, everything works together, harmonies of nature manifest themselves in different ways. And this is similar to other ancient cultures of different regions. But what Pythagoras had discovered was that if something is vibrating, it can create music. So there was this idea that a vibration creates music. And at that time, there was this geocentric model of the universe. So the Earth was in the center, the stars and the constellations and the planets, they were all moving around it. And so as this Earth is in the center and these heavenly bodies move around it, they should be creating music because according to Pythagoras, they were moving, they were vibrating, so they should be creating music. So that's actually where this idea of the music of the spheres came from, was the Pythagorean brotherhood. But then it was like, okay, so if there's music, why can't we hear it? Why why is it silent? Like if we all stay quiet, why can't we hear the music? And so Pythagoras said it's because we grew up on this planet, we're so used to it. It's like heavenly elevator music that we became so used to that we could never hear it. And so that was the idea behind this music of the spheres. And there were many critics of this idea, including Plato, who literally said like musicians have their ears instead of their brain. Like they don't have a brain, they have ears instead. But this idea was so powerful and so poetic that it kept persisting. So it persisted like for 2 millennia, and 2 millennia afterwards, Johannes Kepler, he was really adamant on proving this because he really believed there was like a harmony to the universe. There was this one singular harmony that connected all these different orbits in the universe. And so he made years and years of calculations to look at these planetary orbits. And by that time, it was a heliocentric model, but still there was still that idea that was floating around that maybe there's music, maybe there's this heavenly oscillations and music. And so in vain he tried to like find this harmony, to find these notes, and all these models, they were based on like tonality. So like every orbit was like one tone or half a tone, depending on the type of orbit it was, depending on the type of planet it was. So it was very mathematically structured, but it wasn't scientifically sound, you know. And so he tried, but he came across Kepler's 3 laws in trying that. So that's how the discovery of Kepler's, all the 3 laws happened, was him trying to discover this. So even though he didn't discover it, this idea was still continued. So in The Merchant of Venice, like Shakespeare writes about this type of heavenly music, and this type of idea is still pervasive, I think, in some parts of art. And then it ended up becoming a more artistic, poetic idea rather than a scientific one. But then in the 1970s, there was actually a discovery of like resonance sound in stars. So there was a discovery that stars actually like giant musical instruments. And so this discovery is actually so in line with whatever these people had imagined and wanted so badly, especially like Pythagoras. There's a quote that I've heard, which is, there's geometry in the humming of strings, there is music in the spacing of the spheres. And this is said to be a quote that Pythagoras would say often in trying to understand these things about the universe. And this couldn't be more true today. So I want you to keep this in mind as I go across the rest of the talk. And especially I want you to keep this in mind because we have Starquake Illuminati in our neighborhoods, in Socorro. Yeah, I didn't put that symbol there. I don't know how that appeared on my slide. But we also have some Illuminati at the VLA. Some people may know this person who's Aspen. She's the one who took these photos. But we do have a installation called the Music of the Spheres at the VLA. And so this is all connected partly to what we have around us too. So this idea is pervasive. And so coming back to the idea of twinkling that we were talking about, how the stars quake in space and they twinkle in space, but you couldn't tell them from Earth. So then if you can't tell them from Earth, then how are you measuring these quakes? How are you discovering that stars are like instruments, and how are you doing that? So the way we do that is by using a telescope that is in space. So we avoid the atmosphere, so we don't have the large distortions, and we just have the tiny parts per million distortions that we see on that star. And there's also many other reasons to have a telescope in space. One of them is the fact that like we need something that can look at a star almost like every minute for like a long period of time, like a month. And like we can't use a ground-based telescope for that because the telescope time, unfortunately, optical astronomers don't operate 24/7, but only radio astronomers do. So we don't have the luxury of time like radio astronomy could maybe do that, but it also can't because we need an optical telescope to see star quakes. And so there's no VLAs allowed. Because garden variety stars like the sun, which are basically what I consider the weeds of the universe, they barely shine in radio light. So we need an optical telescope that can be in space, that can look at just one star for 30 days every single minute, and that can measure these tiny star quakes that are like parts per million. And so what does this telescope in space end up seeing? So that's the telescope up there, and that's the star. So we're using the NASA Kepler Space Telescope. And this telescope, this is the first thing it would see. So if you were looking through that Kepler telescope, if you were able to, then you would see this, which is just like an image of the star. So both the X and Y axes are pixels, and you can see the intensity of the star. So yellow is the brightest and blue is the dimmest. And so you can see the stars there. And so Kepler would take a picture like this every single minute. And that's what it would see at one instance. But what is it actually looking at? Like broadly, what would it see? So what it would really see would be these shapes. So these are like spheres and they are moving. So the blue color is when it's moving inwards and the red color is when it's moving outwards. So what the Kepler Space Telescope would see would be a quaking star. And so these are three different ways in which stars can quake. Actually, normally a star quake has many different modes combined. I don't want to use too much jargon, but these are just ways in which the star can move. So many of these ways in which the star can move gets combined to produce one composite mode. So the Kepler Space Telescope will actually see that. That's what this image is actually seeing. And so for the first one, for example, like the one that's completely red, there's only one way in which it's like expanding or it's contracting. So that's the only way in which it can move. The second one, which is blue and red, so like the red part will be expanding, the blue part will be contracting, and then vice versa. So it's like, it's called a dipole mode, and it's just one part is going in, the other part is going out. And then there's a quadrupole mode, which is the third easiest thing to see. And so in that, the center would be contracting, the poles would be expanding, and then vice versa. So that's sort of what Kepler would be seeing. But as I said, like, it's going to be a combination of those. So it's not just going to be one thing that it sees separately for one star. It's going to be this plus this plus this. So it's going to be like this. Okay. So like a star quake is a combination of frequencies. So it's basically multiple frequencies, multiple ways of that star moving. So if you can imagine it, this is in 2 dimensions, what it would look like if you took the surface of the star and put it on a flat table or something. But if you can imagine adding all of these together and trying to think like what that would look like. But now like think of it in 3 dimensions. So think of it like an ocean, but an ocean that quakes in a very specific way. So it's not just like waves, but it's like, oh, like I have to go up and then you can go down and like all this type of stuff. So that's what a star quake would look like. But it's curious to me, like, oh, sorry, I also put the radial, dipole, and quadrupole modes. So these are the first 3 spherical harmonics, like for a 3-dimensional object that is oscillating. So this actually you would also see with electrons and things in quantum mechanics, but I won't go into that. But what causes the stars to move in this way? So it's actually like the structure of the star that is sort of responsible for this. So you can think of a star as a driven damped harmonic oscillator, or in other words, you can think of a star as something that has its own frequencies, but it's also being pushed by other things inside it. And so the star has 3 different regions. This is a very basic diagram, but basically it's like the core, the radiation zone, and the convection zone. The core is where the new elements are formed, and the radiation zone is where the energy is being sent to the other outer layers of the star, and the convection zone is where the gas is rising and falling because it's getting heated up from the radiation zone, it's rising, and then it's falling because it's colder. So how does this structure result in star quakes? So stars, well, specifically sun-like stars, they quake this way due to convection. So they're actually using the rising and falling of the gas to quake in the certain ways they do. So this animation actually shows you the like more than 4 different kinds of oscillations. So the first one that you see is the straight line up and down. That one is the easiest one, which is the expansion and the contraction. So that's actually how the wave moves inside the star. And specifically what I'm talking about is the standing wave that's moving inside the star. And so another diagram, which I've put here, just to illustrate that like every single line that you see here, every ray that you see here is a different frequency, is a different spherical harmonic mode. So the simplest one, which is L equals 0, that one is going through the core. But then there are higher order modes which go across, like, which don't go through the core. And so the different frequencies would probe the star to different depths. So you can understand the star to different levels based on all these frequencies. So I think of this kind of like, and it's convection driven, but I think of this kind of like a musical instrument. So I think of a musical instrument and how like a flute would be a higher pitch than a trombone, or like a trombone filled with jelly is lower pitch than a trombone filled with air. And so that's sort of how I think of this. So if I didn't know the trombone is a trombone, but if I hear a trombone, then maybe I can understand more about how long this instrument is. Or if I hear a flute, maybe I can understand the difference between a flute that's filled with jelly versus one that is not. And so you can think in one dimension of like blowing on a pipe or something. And so you can think of the star in one dimension as an instrument. And so here, this graphic shows you like how the waves would move from the center to the surface. And so just to recap, so this convection, the process of convection, it's actually pressure waves. So these pressure waves are hitting the outer layers of the star. And sound is a pressure wave. So that is why I'm saying it's a musical instrument, because like sound is just a kind of pressure wave. And so basically these frequencies of, I don't want to say sound, but like these frequencies reflect the properties of stars, but you can think of it, the easiest way is to think of it as like different notes or different harmonics. And so you think of it in that way, and that tells you what this instrument is made out of or how big it is. But anyway, that's the little bit about the background. But I wanted to get back to what the NASA Kepler Space Telescope does see. So what you saw there was that image that it took, but this image is taken like every single minute for at least 30 days. And then we get a light curve. So a light curve has intensity or brightness on the y-axis, and it has time on the x-axis. So you can see like there's a lot of data points. It almost looks like noise. But like where is this star going in this plot? So it's definitely not the green one. Because if you look at the green one is on a time scale of days. So like the time period of that is on the scale of days, but these star quakes are happening on the scale of minutes. So actually like the orange up and down lines that you see that look like noise, those are the star quakes. And those star quakes are created by literally like stacking each of these images that's taken in like a minute long intervals for 30 days. And so that's how you get the flux. So they do photometry, or they calculate the brightness of the star from every single image, and then they put it together on this plot. So what about the notes, like the frequencies, like where are those? I don't see them. But the way to see them is actually not looking at this. You have to convert this light curve into something that is more readable, because even though the frequencies are still there in this orange part, but you just can't separate them. So what you do is a Fourier transform. And so a Fourier transform is converting the brightness over time into intensity over frequency. So you change the scale in which you're looking at it. And so then you would see something like this. But this looks terrible, right? To me. No, actually it's pretty good. But like, it would look terrible when I started working on this project, because I was like, this is nothing. But actually, this is the discovery that I'm talking about today. It's just that tiny bomb. So, I mean, this may seem really insane. So let me bring it back to our planet and our solar system. For context, I'll show you our sun. So I've zoomed into that pink region that I highlighted. And so frequencies on the x-axis and power density or intensities on the y-axis. And so if I zoom into this sun, then I can see like this type of Gaussian type of shape. And you can see there's a peak in the middle, there's like a width that it has. But I want to highlight two things. So the first thing I want to highlight is the y-axis. So the y-axis is one of the highest values on the y-axis is 6 times 10 to the 13 parts per million squared over microhertz. But I just want to highlight that number, because that's a huge number compared to what you see later. And I also want to say that for the sun, because it's the closest star, we can actually look at it in segments. So we can see these different higher order oscillations. So remember how I told you that the stars, the simplest three is what I was showing you. I showed you the simplest three because for all other stars except our sun, we can only see those, like we can only tell those apart, because the space telescope will see the star only as a pixel. So it's not going to see it more than like 2-3 pixels across. So for the higher modes that are like very fancy and elegant, you cannot differentiate between this and another one because the resolution is too big. So you can't tell that, oh, that part's blue, that part's red. Like you'll just see an average of that. And so for the sun, you can tell that. So for the sun, actually, we're able to see up to the 18th or the 20th like harmonic, which is a privilege, because most of these measurements, like the star that I discovered, if you look at the y-axis now, it's 40. Like compared to 6 into 10 to the 13, it's 40. So, and again, this is like parts per million squared over microhertz. This is a really tiny measurement. So let me just show you like the maximum mode that we can see with the star, which is this type of oscillation. So we can see the star, like the highest we can ever see the star is like at this range. We can't see the type of detail we could see with the sun. And coming back to a star, like I like to think, like every scientist, like my discovery is 1 in a million. But this is a picture of the star I discovered. I've given it a name. The name is Papayu. It means papaya in my mother's mother tongue. The official name of the star is KIC 110295516. But since I'm an astronomer and since I'm writing a paper on it, I can just name it whatever, and everyone who cites my paper has to follow that. So I actually named the star, yeah, and I didn't spend like $1 million. But this star, I also think it's 1 in a million, not just because I discovered it, but also because it was hard to find. So this is, again, that oscillation that I'm talking about. That's the star quick. That's the thing that I had zoomed into and shown you. And I have it on like official notice by Vincenzo Quaxano, who's a duck at the Macy Center Duck Pond, affiliate of ducks at Universities Incorporated, and also a member of the Pythagorean Brotherhood, that it's a quake, not a quack. And these immortal words are what helped me get through, the pain of looking through 5,000 stars to find this one star. But I also want to point out some other thing, which is a huge source of noise, which is the background of this star. So Papayu's background has been a nuisance. So this background noise is actually what you call granulation, stellar granulation, or in other words, it's just gas bubbles that are hot and they burst on the surface. So the convection makes the hot gas rise, but then like what if it bursts? So this just creates like a lot of background noise. So the reason we don't discover many of these star quakes is not because like Kepler's doing something wrong or because we are doing something wrong. It's generally because the star is just being too active, or because maybe the star is in a binary system. So these type of stellar activities, they actually suppress what we can see about these oscillations. So most stars in the universe, especially all sun-like stars, they are quaking. They are quaking for sure. We just don't know if they are, because many of them have high levels of magnetic activity, high levels of like binaries, and so we're not able to tell. And so in terms of the discovery, Papayu is found now, but why wasn't it found earlier? That's because earlier we had some data processing issues with the Kepler pipeline. So earlier the Kepler pipeline was only looking at that aperture, a smaller aperture, but then later it looks at the entire field of view. And so you can see an oscillation is now there where one wasn't. So the reprocessing has unearthed like a treasure trove of data from Kepler. But going back to sort of these frequencies. So frequencies are really essential because having accurate frequencies means you get an accurate age of the star. So the pink line you actually see here, that's the statistical fits I made to the frequencies. This is by using a software by Enrico Corsaro. And so this gives me really accurate frequencies, but also like how do frequencies help me? So I've spoken informally about like oh, if you have frequencies, you can know how big something is, or if it's filled with like jelly or whatever material it's filled with. But like, how do I get age from frequency? So I want to take you back to this drawing. And so in this drawing, remember how I was telling you like the different modes will probe the star to different depths. So the radial mode, which is the easiest one, that one just goes up and down through the core. And so that's represented by this frequency here. So that red one is the radial mode. And then the quadrupole mode, which is which is the third one that we can see, like the last one. That one does not go through the core, but it goes through the surrounding areas. And so that's represented by this peak in the frequency. And so the separation between both these frequency peaks, this actually tells you a lot about the age. So this correlates really strongly with the stellar age, because it's caused by the travel time of the waves in these different depths, and it's also caused by the density of the material. So the travel time and the speed is all affected by the densities and how thick the layers are. And so that can tell you about the evolutionary stage of the star, because when stars grow up, they form heavier elements, and also like the depth of the layers will change. So this is the field of astroseismology, which literally means a star that is shaking. But it's kind of like an X-ray. I think of it like an X-ray, where like you can look into the human body, you can see how old my bones are or something, but like you're just looking through me, sort of. And so that's what astroseismology helps us do. It's actually similar to what we do with like seismology on the planet during earthquakes, is like when we discover the Earth structure using earthquakes. So that's astroseismology. But there was also a part of my talk that was about twirling. So I covered the twinkling, which is the astroseismology, which is these oscillations. And these oscillations gave me a really accurate age. So Papayu is like 4 billion years old, which is 4 gigayears, which is very similar to our sun. But there's also the twirling, which is the rotation. And so rotation, another word for the rotation that I'm using, it's called gyrochronology. And that's basically using the rotation period of the star to get an estimate for its age. So for Papayu is rotating every 21 days. So every 21 days, Papayu rotates and comes back. But then Papayu is quaking like every 2 minutes or something, or 8 minutes. So it's like rotating and quaking. And the way we measure these rotations is actually because of the spots that are there on Papayu. So like when the sun has a spot, the brightness of the sun decreases a little bit. So that little brightness decrease can be measured across days and years. And so that's what we've done with Papayu. So we have 15 quarters of long cadence Kepler data, and we have a very well-constrained rotation period measurement. So rotation, I just want to point out, in that power spectrum where intensity is on the y-axis and frequencies on the x-axis, rotation is also a form of variability. So in most of my my talk, I zoomed into like this region, but actually like there's so much else going on. And so this rotation period, it's a low frequency form of variability for the star. And so I actually cropped it out of all my plots. That's why you didn't see it. But I want to say that it does exist. And so if you look at the oscillations in comparison to the rotation, you can see like how small it is. And then there's also the stellar noise because of the bubbling. So this is actually what a real like power spectrum for an astroseismic rotating star looks like. But we just focus on what we need, which is the frequencies. So now I just want to point out that these are on different like levels of time. So the oscillations are on the order of minutes, the granulation is on the order of hours, and the rotation is on the orders of days or months. Just to show you that it's moving from like a low frequency to a high frequency. And then also, now that we're talking about rotation, why does rotation matter? So the idea is that as stars age, they're rotating slower, but like how exactly are they rotating slower? So there's this idea that there's magnetic braking happening inside stars. To be honest, stellar physics around this topic is really not well known. So it's really not something I can talk too much about. but I can just say that stars have magnetic fields. These magnetic fields slow them down as they age, but there's different ways in which they could be slowed down. So we've had two papers recently in this field of gyrochronology, and these papers really like show strong evidence for weakened magnetic braking, which is that it's slowing down, but it's slowing down slower than you expected. So it's not slowing down as fast as you thought it would. So like suppose I'm an aging star, and first I was like moving at like I don't know, like 2 days, but then I'll become like 20 days as I'm growing older because it's taking me longer to move around. But then in stalled spin down, it would be like if it was at 2 days, then it's like, oh, maybe like 30 instead of 20. So we don't exactly know where that limit is. But we do know that it becomes slower as it ages. So why do we need to know the kind of rotation these stars do? Why do we need to know the relationship between rotation and age? So that's because if you look at the rotation period, which is the y-axis, the idea is like in the future, we can just look at the rotation period and tell you some star's age. But like here, depending on which model you choose, depending on which braking law you are selecting, you can underestimate the age by 3 gigayears. And for context, like Papayu's age is 4 gigayears. So that's like a huge error. And so the way forward is that we need to have more rotating stars that have accurately measured ages, so we can constrain this law and we can know which law is right. And so that's where like Papayu is important, because this is Papayu amongst stars that are rotating, but they also have like astroseismic ages measured. So the stars in black, they have a known rotation period, and Papayu also has a known rotation period. There's only 10 of these black stars, and so there's only 10 well-constrained astroseismic rotators. Papayu is the 11th data point. And if you look closely, this is the sun, and this is an evolutionary track. So this is telling you that like Papayu is similar to the sun in certain ways, not in every way, but in certain ways. So it is actually a really unique data point that we have here with Papayu. And as we know, Papayu is 4 gigayears old. I've now put it on that plot with the period on the y-axis and the age on the x-axis. And so you can see that in terms of those models, like Papayu is literally at the cusp. So it's sort of the one data point that we have that is at that cusp. And it's like a benchmark star, which anchors where these models diverge. And since we have such little information on stars that fall on these models, since we have such a small data set, it's good for us to have something that can tell us where that physics changes. What kind of star is it that would follow one over the other? And so this is actually a subset of stars that are close to Papayu in terms of their temperature. So they're color coded by temperature. That's actually the ZAM's temperature, but I didn't want to go into that detail. But yeah, so this actually shows that there's a preference for the weakened magnetic braking, which is the stalled spin down. So the spin down is slowing down. That's what this paper and this work also shows. But so basically, in short, I'm not sure about that, but this may be. So that's my conclusion. But I want to go into a bit of a minute to tell you like why this is important. So often like we think of stars and this kind of thing that I'm doing, it's like such a small subset, such a small field. It's many recent developments. But if you know your star, you can actually know your planet. And the whole idea, the whole overarching idea is like in the future, we'll be able to just know a star from its rotation period. Just measure some star that has like some spots modulation, and then just say like, oh, you're like 20, you're rotating at 20 days. So okay, like your age must be like 4 gigayears or something. So like in the future, that will be a much more easier process, and that will be a much more quicker process, and that's the future we are hoping for. That's not the case right now. Right now, if you want to get the star's age, you can't use rotation period. You have to do an astroseismic age measurement, because that field, that connection between both the fields is still not robust. But in the future, we hope it will be. And knowing your star is really important for knowing your planet, because as we know, like we are on Earth, we are adapted to our star, which is the sun. So if the sun was a different star, we would be different. Our planet would be different. So if you know your star, you can know your planet, and you can know the future of humanity, the future of other worlds. And so it's a really exciting thing to be a part of. And it has a lot of unknowns, but there's something more to be uncovered. And I look forward to the time when we can actually discover that. So in summary, I'm just going to leave my summary slide out. But I've discovered Papayu. It's close to the sun in certain ways. It's at that anchoring point, and it helps us know a bit more about the physics that's happening between these two models. Yeah, so that's the end of my talk. I want to thank you for coming, and thank you to a lot of people in this room who supported me. So thanks for being in my life. Thanks for inviting me down, and thanks for being on the Zoom and being in person. So I'm happy to take questions. Thank you so much.
Yeah, I was wondering if those light curves and starquake, the Fourier transform you showed, is that a continuum broadband emission, or is that in a spectral line that Kepler is looking at?
So it's not spectroscopy, it's photometry though.
The photometry in just the white light, or?
Oh yeah, like so it's that's a good question. Oh, so you just mean like what wavelength is it doing photometry in? So like optical? Is that what you meant?
No, I meant is it looking at a spectral line Doppler shifts, or
No.
just
No,
continuum
not
photometry?
Yeah, just like simple photometry, like aperture.
Does every star shake in Kepler amount?
Oh, like the quakes?
Yes,
Yeah,
it's very
most-
common. You see almost all
Yeah,
stars
it's
in
very
Kepler.
common, but like you won't see it though. So like we know
It's
it
below the
exists.
noise.
So like sometimes in most of the stars in my sample, which was like 5,000 of them, they had like above 90% detection probability to detect the astroseismic signal. So you can calculate those probabilities based on like the stellar properties that we know. But like even after getting a 90%, like, oh, these are all great candidates, but like looking at them manually, you don't see it. So there's no other way. Like you have to do manual inspection for every single light source and power spectrum. Yeah.
So how does mass of the star play into all of this? Is there a direct relationship to what we can see for the star quakes in regards to mass, or has there only been a focus on a certain mass range for the stars?
I would say like this is for, well, they do have astroseismology for different stars, like at different evolutionary, like red giants and stuff too. But in terms of most of the work that's been done, it's mostly around like solar type stars. But in terms of mass and how it affects the spectrum that you would see, it definitely affects the frequency. So I didn't show this, but maybe I will show it now. What's this? Okay, so there's actually another frequency separation. It's called the large frequency separation. It's the difference between two frequencies that have the same spherical mode, like the same L. And so that actually scales with the radius and the mass. So that scales with the density. So basically, the average density of the star would affect that. And so when you're finding the preliminary age of the star, you're actually plotting these frequency separations against each other on what's called like a CD diagram. I have a picture of it, but it's not on my slides. But I can just show it to you. Which is this.
Okay.
Yeah.
Yeah. Okay.
And so on that diagram, you can see that the age of the star is determined by these separations. So the mean density would affect it, but also the radius. So it's sort of like not exactly 1-to-1, but it definitely has an influence.
Okay.
Does that answer?
Yeah, no, it does. And so does that also mean that if you were trying to convert this to be able to use the rotational period is an effective age that also has to have a mass range limit in order
Yeah.
for that to actually work though,
Yeah.
right?
Yeah, that's a great point, because a lot of the, so in this plot, which is actually from this paper. So in this plot, most of these stars are younger ages. So we need more stars at older ages, and we need more stars at that cusp. So now we have one star at that cusp, which is Papa U, but we definitely don't have stars at all stages and ages, definitely not. This is biased towards actually like open clusters and younger stars. So we need to change that.
So you mentioned there's only about 10 stars with this rotation
Mhm.
age estimation.
Yeah.
So the number is small, it's because there's just like the mass range limit, or because it's a new tool?
I would say it's small because, so like there are stars with ages from different methods that are rotating, but like in terms of the most perfect age you can get, this is the best way to do it, which is the frequency way. Because so like if, like when I said 10, those 10 are like the ones that have like really robust rotation period measurements that have been checked with multiple ways, and also have like astroseismic measurements for the age. So that's what I like, that's why it's a smaller sample, but it's also smaller because we haven't been able to find that many astroseismic oscillations. Yeah, so we're still looking, but like I don't know when it'll increase like a huge amount as such. Yeah, it's just gonna happen slowly, because I think so far like this plot is from 2017, so it hasn't changed that much, you know, and it's 2023 now, so I think it's just gonna take time.
So can I get a conclusion that this method is the most accurate
Yeah,
estimation of star age?
yeah, it is. Yeah. Any other question?
So what's the limiting factor of making this go faster or better? Is it a matter of going through more data at a faster rate, like with machine learning or something else, or is there another thing that's the limit?
I think right now a lot of the stars that even have high detection probabilities, it's just luck, I think, because the stellar activity is so high for some of those stars that you can't see the oscillation, and if you can't see it, you can't measure it. So I think, I mean, with the bigger telescopes and stuff, we can definitely probe a larger amount of stars, and so the amount we find will be larger too. But in terms of like increasing the chance for us to detect, that's sort of not up to us. Like, you know.
We have a question from online audience.
We have one in-person question there.
Oh, okay.
Yeah.
So can you use this to constrain other aging methods that you can use for things that we can't really measure, like the binary star systems?
So like use this to measure a binary star system? Like how will it?
Because you said that we can't use this method for, is it binary star systems?
Yeah. I mean, we can, there's still ways that you can use those frequencies, but it's just not gonna be the same way that I did it. So you can use like what's called mode splitting, which is basically the frequency difference. Like sometimes you can see a shift when it's an active star that's rotating. And so that difference can also give you insight. But yeah, in terms of binary ages, I'm not that familiar with using this for binary stars. But I definitely know that's like most of the work that's being done right now is like solar type stars. And like binaries are sort of like, it's like the error part of our work, you know. And so like we can do it, and I mean we can find ways around it, but I don't have a clear answer of what that looks like. Yeah.
Ching, you may ask your question.
Yeah.
Thank you for the talk. I'm wondering if the oscillation signatures would be stronger for pull-on stars.
So what stars?
Or
the-
stuff.
Polar. I don't know the answer to that, John. I think there's definitely the rotation changes between the poles and the equator. So I know like the equator is generally moving faster than the poles because most stars have that magnetic field with a differential rotation. But in terms of measuring it from the poles, what you would see would be different. Like so what you would see, for example, for like the dipole spherical harmonic, maybe it would look radial to you, but it's still captured in the light curve. So I don't think it would make a difference if it was if the inclination was different for the star, because you could still see the variability for most of it. So I don't know if that answers your question, but yeah, I'm happy to think more about it.
Thank you.
Thank you for asking.
Okay, then let's think.
Okay.
Vanshree again, and we have a new student here. So Anna, we want to introduce.
Oh, yes, sorry. Please introduce it. So we have a new international graduate student that is visiting from Poland, Sagar. But Sagar has been here before for the data reduction workshop last year, so some of you may met him.
Hi, I'm Sagar, and I am working on evolution of radio galaxies, especially on giant radio galaxies. And I have worked. Nice to meet you.
And Sagar will be here until end of September.
Who are you working with?
Me.
Oh.
Wasn't that obvious?
Okay, so I guess it's over.
Yep.
Thank you.
See you next week.